software construction. And in simple terms, what software construction means is how do you program what you have already architected. So that's what we're going to focus on today. So by hands, how many people have programmed a full project, maybe a website or a web app or anything, or a simple project like a calculator or to-do app? Anyone? Hands up. So we have all done that. So this is a very familiar topic, so I'm not going to focus mostly on that, but I'm going to have a walkthrough, and we are going to move to the practical session. Not practical session, but the code lab. We are going to continue with what we started last week. So today I'm going to be talking about software construction. Another question apart from the code that you have wrote, how many people have vibe coded anything from scratch up to until completion, full vibe coded up? So I see a few people. So today, because of AI driven programming, I know most of you have used AI tools to program, maybe Casa or Cloud Code or Codex, to maybe do some prototyping or vibe code something or a project, or maybe to debug or something like that. And I was privileged to have purchased a Cloud Code Maximum this week. So I've been trying to see how much I can get from the output from the Cloud Code. And I've seen that you can do a lot of things. You can build, you can develop a lot of things. But apart from that, I'm going to focus on the basics and foundations of coding. So why are we talking about software construction? So before last week, we talked about architecture, but we did not talk about the SDLS, how we are going to focus after you have architected the software. What do you do next? Do you first write the specs? Maybe for those who are focused on AI-driven development, do you write the specs? Or do you first prototype, then you debug later? How do you do it, the software development life cycle? How do you continue with that? So that's what we're going to focus. 60 and 70% of engineering hours live. It's where most defects are introduced and most are caught. It's where architecture meets reality. It's where junior engineers grow up and senior engineers earn their keep. So this is where this part of software construction is where most of the development work happens. And those who are not keen on developing production level products or production level code, this is where you focus on 100%, because you are not focused on reliability or the other things that you focus on when you're architecting a production level software. Maybe if you are doing a simple thing, this is where you are going to focus on 100%. So, but if you are focusing on, for example, a client project or your own startup or product you are going to take to the market, this will take 60 to 70%, because the other part is the architecting or the preparation, the design and all that. Then the other part is where you're going to debug on debugging, testing, and deploying. So that's where the other percentages of your work will take place. So we are going to focus on the 60-70% of engineering hours. That is coding. So we're going to first speak about something about if you do something wrong, how it will cost you. So in August 2012, Knight Capital, one of the largest market makers on Wall Street, they deployed new code that morning. It went out to 7 or of their 8 production servers cleanly. The 8th got missed. Here's the part that matters for us. The new deployment used a flag that meant something different in the old code. So on 7 servers, the flag triggered the new logic. On the 8th, it triggered a dormant test routine from years earlier. Alafu routine, it messed up and they lost $440 million. And the company nearly went bankrupt. So it's very important how you take this part. So how you do this part is going to determine how you are going, how the project will be. So any mistake you do here, it will cost you. So the last week we discussed about architecture, how anything that if you architecture something that is not reliable, it will cost you. But here, if you do any mistake, maybe you code something that's not right, or that maybe used a JavaScript and you not enforce type, something like that may cost you in production. So this was something that cost them. So as last week we discussed that the whole history of software engineering is a rising level of abstraction. That's what we talked last week. So today it's also true, because most of the things that you do, for instance, I don't think anyone has programmed most of the things. Maybe most of the work you do, you just import libraries that have already been programmed, then you integrate to your code. I think that's what most people do. You just integrate. For instance, you might integrate something like Redis to do maybe something like caching or something like that, or use something that I'm trying to find a good example of a library that you can use that is abstracted. So it's the same thing. The way that the architecture is a rising level in abstraction, the same way in engineering. So most of the things that we do is just integrate libraries. And with AI coding, it's more abstracted because you write only specs. You don't write the code itself. You just write specs and you review what the AI agent has produced. So when I'm going to talk about the 4 fundamentals of construction. So our guide for this event, rethinking software engineering, is we are using the SWEBOK, the software engineering body of knowledge. It's where we are going to be getting the most of our content from, that book, because we want to be up to date to what the standard is out there in the software engineering, so that we can bring the same standard to here. So that's the book that we're trying to use, and that book specified 4 fundamentals. And I'm going to walk through each one and each of them, and I give you a way to spot in your own work. Here are they. So the first one is minimizing complexity, not maximizing, minimizing. The second one is anticipating change. Third one, construction for verification, and the fourth one is reuse. So these are not techniques. They are not best practices. They are not techniques. They are not patterns, but they are the underlying physics of construction. So these are what should be your guiding principles, or the things that you focus on when you are constructing your code. So you minimize the complexity as much as possible. Don't overcomplicate don't over-engineer your app or your product. Anticipate change. For instance, if anyone has ever used Angular to program his front end, you know that they release almost two releases every year, and it can mess up with if you have not anticipated for the change, it can mess up, because when you try to migrate, you lose some things. So you always program when you're programming or you're constructing the software, you always anticipate the change. Then you construct for verification. So this point is where what mostly talks about is you code something that can be testable, so that you don't test on production. No, most of us test in production. Maybe you program the whole thing, then you go and you deploy it, then the users give you the feedback. That's how you test your solutions or your products. But you construct for verification, then you reuse as many things as possible. So the single most important goal is minimizing complexity. Complexity is the side effect of the work, is the enemy you build against. So let's focus on the first fundamental. And the science behind this is that human working memory holds roughly 7 things at once, plus or minus 2. That's it. The entire bandwidth your brain has for reasoning about code in the moment. So when you are coding, what you programmed last week, you will not be able to remember when you are maybe debugging this week. You might not remember everything that you are doing at that time. The context had already changed. But if you have had minimized complexity, or your complexity was to your lowest, it's very easy to debug or to continue with the code. But if you have complicated the whole code at the beginning, then when you're trying to debug or do something else, you're going to have challenges. And I've tested this. It has cost me. So when you write a function with 12 variables and 4 nested conditions, you have exceeded the working memory of every developer who will ever read, including future you. So I don't know how many of you have ever programmed a UI, and sometimes the HTML can become so nested. It can become very big. And when you add other things like inline CSS, it becomes even more complex. And if somebody comes and tries to debug, they might break something in the whole app. And that's why we are saying that we should focus on minimizing the complexity. So every defect that has ever shipped, every off by one, every null pointer, every race condition happened because somebody working memory got overwhelmed. They forgot a case, they missed a branch, they thought the state was X when it was actually Y. So when we say minimizing complexity is a master principle, what it says is, what's really saying that write code that fits in a human head. How do you spot violations in your own work? A clean test. If you have to scroll the function, the function is too long. If you have to draw a diagram to explain to a colleague, the abstraction is wrong. If you can't name something cleanly, you don't understand it yet. So you must understand your code fully. And if you cannot understand some things, like for instance, what this function name means, what this function does, if this function is too big, then you have already completed the whole system. Your functions should be readable. For instance, a simple thing like a variable name should be very explainable. Like for instance, if your function adds 1 plus 2, you should write a function add 1 2. I don't know how you write it, but it should be very explicit so that you can know. Don't just put something generics that you can forget. And so if somebody has written an addition function and it is not doing addition, or it is doing more than addition, then it becomes very generic and it can complicate the system. So the second one is anticipate change always. So what we mean by anticipating change is that a software that you write yesterday might change even today. For instance, some tools like JavaScript tools, they evolve very fast. And you might code something in React 17, then React 18, it changes. And the context also can be outlived. So the team will change, the business will change, the requirement you carefully captured will be wrong the next quarter. So you might program something, like for instance, if you program a login function, but when you go to the market, people are suggesting that you use signing with Google or something like that. Or for instance, if you have programmed any mobile application, Apple has changed a rule that if you are signing with Google, you also sign in with Apple. So something like that, after you have programmed your whole code, then you're going to deploy the mobile app, you find that it has that change. So if you have not anticipated a change like that, it's going to cost you extra time when you're going to reconstruct or something like that. So when you are constructing and when you are making the small line-by-line decisions, you have to be asking what here is likely to change, and have I made it cheap to change or expensive? Look at the example, like here. When you had got the tax rate, it will change. Like right now, I've seen that the tax rate is changing with the new finance bills changing. So anticipate something like that if you're programming something for businesses. Another thing, if you wrote the third-party integration inline, the API will change. They always do versioning, deprecation, rate limits. One database for everything, scale will change. What works at 1,000 users breaks at 1,000,000. So also the decisions like how you have programmed the database, what the ORM that you have used, it will also affect how you do it. So 3 copies of the same logic, only 2 will change. The real horror of duplication, not the redundancy itself, but the fact that it drifts. None of these are about predicting the future. They are about respecting the fact that the future will surprise you. So construct in a way that you anticipate the change. So fundamental 3, construction for verification. Some things are easy to miss. Like for instance, you might code something that maybe you were not very sure of and you have not verified. So if you don't program something that can be verified, that's easy to verify and easy to test and easy to find something, then it might break something. And this is as simple as writing things like types for your, maybe if you are using JavaScript, maybe types and assertions, clear names and structure, tests written along the code. So things like test different design and things like that are going to help you when you're trying to verify your program. So use types, use assertions and things like that. So good programmers write good code. Great programmers borrow and steal and use. So this is the 4th fundamental. You must reuse things as much as possible, because as much as we want to write everything anew, afresh, and there are some things that have already been solved. And by importing a library or using a library that somebody has already programmed, then you have already abstracted that part. A simple thing like using Axios for API calls and things like that, so that you don't focus on that, you just focus on the other things. So when you are in your career, you always write everything because you want to prove that you know something, or you want to understand something from the ground up. But you have to know that most of the things that are used, and that's why the something like NPM node modules are always being updated and being created, because people are solving issues that they have already experienced. So you don't have to redo the things that others. You don't have to reinvent the wheel. If somebody has already done it, you just reuse. So these are the 4 fundamentals: complexity, change, verification, reuse. Everything else in this talk hangs on them. So the practical surface. So we are going to see the practical side of it. So the 5 themes hold in your heads. 1, designing in the small. 2, defensive construction. 3, specialized techniques, quality building, and construction stack. So our guide, the SWEBOK, the software engineering body of knowledge, has highlighted the 5 themes to hold in your head. 1, designing in the small. API design, construction level design, generics, object-oriented runtime issues, the decisions you make about a function, a class, a module, or the system. 2, defensive construction, assertions, designed by contract, exception handling, fault tolerant, code that protects itself from misuse, include misuse by future you. So a simple thing like exception handling can be very, for instance, the try-catch part of the code is very important because it might help you not misuse the code. So 3, specialized techniques: text machine, table-driven code, ground-based input, concurrency, middleware, distributed and cloud-based construction. Each one is a tool you reach when the problem shape demand it. So some things need specialized techniques. 4, quality building. You need testing, integration, test-first programming, performance tuning, the work that turns construction from typing into engineering. So some things like, for instance, how somebody logs in, the auth module. If you have ever programmed, you know that the auth module can waste a lot of your time. So if you can build that thing for quality, like for instance using OAuth or using the magic link thing. It's very important because you are building for quality so that your users cannot be forced to do other things, like for example forget password, things like that. If you use something like magic link, then you skip that process. So 5, the conceptual stack, your ID, your linter, internalization, cross-platform, concerns, visual programming, low code. So how you construct it is also very important. The tools that you use, like for instance, if you use Vue versus Angular versus React, the 3 have different things. So like for instance, if you use React, it's very good if you want to increase, maybe collaborate with others, because React is widely known. If you use Vue, it's very stable and very easy to use. If you use Angular, some people might struggle with it. So things like that, your conceptual stack is also important. So you don't need to be an expert in all 5. You need to know they exist. So when a problem walks in, you reach for the right category instead of inventing from scratch. So what are the best practices? This is a take home list. I want to be honest with you, there are no shortages of best practices lists in our industry. Most of them are wrong, dated, or generic, or useless. Like 1, test early always. Another thing is name things clearly. The third one, manage dependencies deliberately. So these 3 habits are going to make sure that you become very good at what you do. These are like my top best practices. So if you test early on, you will anticipate the changes and other things like debugging and all of those. The other thing is naming things clearly so that you can reduce complexity. The third one is dependency, managing your dependencies. For instance, the libraries that you use, simple thing like the icon pack that you use for front end and other things like that are going to be very crucial. Like for instance, if you are very good at mobile programming, you know that if you program the mobile with many dependencies, your app will be very heavy because every dependency comes with its own specifications. And the more things that you add, the more heavy your app becomes, and you might find that you don't need those libraries. So you must be very deliberate on the dependencies that you use. And also things like, for instance, the state management that you use, zoo stand versus Redux, things like those ones is very important. So these are there are 7 more best practices that you can go and find out. So go and find your best practices and list them so that you might be, when you're programming, even when you're vibe coding, you might know what to do, what you're going to enforce in your code and things like that. So these are these one are habits, not rules. You pick them and become your default. But if you can carry 3 out of this room, carry these 3. So the other ones are standard formatting and convention, investing in legibility, build verification to the code, not after it, treat documentation as part of the construction, measure defect rate, no lines of code, resist premature abstraction, keep learning the fundamentals. So the last one, keep learning the fundamentals, is also important, where the more you learn how the thing works behind the abstraction, the more you understand the thing. Like for instance, if you try to learn what Axios does, you might know why it's important and what you're trying to solve by using it. So things like that, you learn the fundamental, resist premature abstraction. Like for instance, don't use libraries and if you don't know what they are doing. So the elephant in the room, theory is great, but nothing makes an idea stick like seeing what others are doing. And we are going to talk, the elephant in the room is AI. Now because AI has come and people are using Cloud Code to program a whole program, you hear many people saying that they've lost job to AI. So you might wonder, why are we learning about this if AI is going to take our jobs? But I don't think it's true that AI is going to take our jobs. I think AI is going to accelerate how we are going to build things and how you are going to solve problems, how you are going to iterate fast and things like that. But the fundamentals and the best practices, they remain. So even though AI will come to change the industry, I think it's going to affect how we do it, but not the fundamentals. The fundamentals still remain. So, not autocomplete, agents that read your code base and plan changes. So, AI get used for everything from autocommit to existing threat. Like for instance, ChatGPT has released something that is going to look for bugs and cybersecurity things. So it might, news like that might disorient you because you're thinking, if this is doing even cybersecurity, then what are we going to do? So the new is not autocomplete. We had autocomplete for 30 years. The new is agents, systems that read your code base, not just the file. The systems that plan changes across multiple files, systems that run your tests, see what fails and try. Cloud code, cursor in agent mode, things like that. So the shift is from a tool that completes your line of code to a tool that takes a task and tries to finish it. So why learn these things if AI is it does all the other things? So the new construction skill is not writing, but reviewing. So if AI can write most of the code, like things like that, your work will be reduced to reviewing the code. You review what the AI has written, then you change and you introduce the best practices that you have already set up for yourself, like the habits. You make the AI code as if you are coding it with it, like you're pair programming with it. So you are reviewing and doing the other things. So fundamentals outlaws every tool we will ever use to write code. So even though we have moved levels of abstraction, like for instance, in the past we used to have machine code, then you move to assembly, then to high level. The more we going higher level of abstraction, the fundamentals still exist. Like there's things like memory affect everything. Things like exception handling, things like that. Those are fundamental things that will not change even if AI writes the code. So if you focus on the fundamentals of software construction, then AI is going to accelerate what you are doing. So you should not fear the future, but you should prepare for it. You prepare a way for writing less code, but also knowing what the code does, so that even if AI does something, you can know. Sometimes AI, I've struggled with this part in AI. AI can guess something like hallucination. It can hallucinate a whole library, and you try to debug, then you find it that the library does not exist. So it has wasted your whole time. So things like that. So if you know the fundamentals, you not struggle with things like that, or you write code that breaks in production. So the fundamentals still exist, and that's what you should focus on. Because right now, if you focus on the coding and the other things that AI can do, then you'll be lost and you not adapt to the change. So I think I've completed what I wanted to say. If anyone has a question, you can ask, or we can discuss on the changes you have faced when writing code, construction, how AI has affected you personally. So who here has been affected personally by AI? Like it has changed his life. Maybe you have been to a kazi or something like that, personally. Or it has changed how you write code. Like for instance, has anyone moved entirely to AI-driven development fully in their job? Or you are still writing code like cavemen? So if you have any question or anything that you might want to raise, I think this is the time. So thank you for listening to me, and I hope that as we move on to the practical and the hands-on section, that we learn more and see how we are going to, which fundamentals we are going to focus on the hands-on session. What are the things that we're going to to see that we differentiate and how we are going to evolve around that. So I think